Okay, so the next video is to talk about the difference between analog and digital signals. So, two signals that you're going to encounter when we discuss things in this class are analog, one in which a signal that varies continuously in time, and digital, one which is a signal that has discrete values assigned to it. Okay, so you have a page there that gives you some examples of what these signals look like. What ends up happening, all right, when we create a digital signal, in other words, right now my voice, while I'm here in my room, it is analog as I hear it. But the way that you guys hear it right now is going to have been processed into a digital signal in the computer as it's being recorded, transmitted into YouTube, okay, and when it's played back on your laptop, the signal is then converted again from a digital back to an analog signal. And so what's happening is that we have a sampling that's taking place. In other words, the signal, all right, my voice going into a microphone might create something that looks like this on this page here. It's this continuous curve, right, that goes up nicely like this, all right? And so that, is what my voice looks like. It looks like a proper sine wave or some combination of multiple sine waves. So what happens, the computer cannot take an infinite amount of information. It has to take only pieces. It can only take so much. So what ends up happening is it takes a sample every 10,000th of a second. In other words, the sampling rate given here, 10,000 hertz, means 10,000 times every second. All right. So it takes a sample of, we'll say the volume of my voice, okay, or maybe the frequency, and so once every tenth of a millisecond, right here, okay, that's the sampling rate. Okay, so once every 1/10,000th of a second, okay, that's what this 10,000 hertz tells us, all right? So the above signal, okay, is going to be sampled then at all those times, all right? So what we end up with here is a sample being taken here, and actually even at time equals 0. And all the way through. And so we can record what all of those voltages are being generated, all right, in this microphone. So what we have would be 0, 4.5, 8.7, 12.0, 14.7. These are just the values that I read off of this at all these times. Might not be exact. 15.0, and then the same way down here on the other side. So what ends up happening, all right, is that we can say that we'll encode this signal will be encoded with 3 bits of information, okay? So if the signal is encoded with 3 bits of information, the question is, how many different levels of information can we have? Signal encoded with 3 bits, sorry, I should say with 3 bits of information. So what this tells us is that we have 8 possible levels of information. Okay, so what ends up happening is that we typically would break the voltage signal evenly, saying if it's between 0 and 2 volts, okay, we're going to assign this 0, 0, 0. And then we go from 2 all the way up to 4 volts, and we would assign it 0, 0, 1. And we're going to keep doing this up until 16 volts, which is the range of our signals here. All right? Let's see here. 6, 8, 10. Okay, and so all of these would be 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, excuse me, 1, 1, 0, 1, 1, 1. Okay, so these are all the levels of information that we can have from this voltage signal being produced in a microphone. All right, so if we convert this into binary, all right, what are all the values that we would have? Well, we just use that table, and this signal will be 0, 0, 0, this will be 0, 1, 0, this will be 1, 0, 0, this will be 1, 1, 1, then 1, 1, 1, 1, 1, 1, okay? Oh, excuse me, I missed one. I mistakenly wrote this here. There we go. 1, 1, 1, 0. Let's see, 0, 1, 0. Nope. 100 there, sorry. Okay, so what this does now is that this ends up changing what the signal is. Okay, so before when I told you that my voice gets converted to a digital signal, and that signal is then sent, through the internets to your computer, and it's converted back into an analog one when it goes through your speakers. Okay, that it has to be corrected into what it probably looks like. It probably looked like originally, but it's never going to have that same quality. So it's an interesting thing, we have to, what can we do to improve the reproducibility of digital signals? Well, you can have, a small time division. You can also have, many bits to store the information. There's many different ways that you can go about this, right? So that's pretty much what the difference is between a digital and an analog signal. Make sure you read in here the different types of digital and analog technologies in terms of information storage, okay? They have their photocopying and vinyl music and cassette tapes and all these different things. And your textbook as well has some descriptions of the pros and cons of using each one. You are going to be required to know that for this class, okay? So that's pretty much it for digital and analog technologies as far as the way that the information is stored in terms of just the information itself. But in a physical sense, the way it can be stored, we're going to talk about here for CDs and DVDs, okay? So you have that page there that has the diagrams on it, exactly, it explains exactly what's happening. But what happens is that you have a laser light coming down, okay? I'll have it pause the video now and you can read the first half of this, but once you've read it, all right, the computer can read a 1 or a 0 when the laser light, which is reflected down here, gets to one of these edges, all right? And what we end up having happen is comes up here, and at the edge, it bounces up. And if it bounces up at the edge, it interferes with both of these beams right here as they go back up. All right, if they interfere, all right, and the reflection there is at the edge, they'll have destructive interference, and they'll know to read a 1. Otherwise, during the flat parts, they know just to have 0, and they, just read that based on the timing, okay? So anytime it hits that edge, it's going to read a 1. Kind of just like when we watched that video about the hard drives, when it switches the magnetic domains, they know to read that as a 1, all right? So how do they know, that the laser light has gone over the edge of one of these lands or pits? Well, the idea here, okay, is that both these beams come up. And if both these beams come up, all right, and their path difference is lambda over 2, well, that's the path difference for destructive interference, okay? And so what happens here is that this second beam, all right, will have traveled a shorter distance, and the path difference is going to be approximately whatever this depth is, all right, times 2. So delta L is going to equal the depth. That's the depth right there times 2. And so what we can do is we can set both these equations equal to each other. All right, we have 2 times d is equal to lambda all over 2. And the construction for destructive interference is that the depth of this pit has to be equal to 1/4 of the wavelength. All right, so this is a condition for destructive interference right here. All right, the difference between the two light beams, the path difference, is this. All right, d times 2. And it shows you there that d is equal to lambda all over 4. That's what the perfect depth of the pit would be based on the wavelength of the laser light. So if we have the depth here is 150 nanometers, we know that the wavelength of the laser light used to encode the data should be 600 nanometers, all right? And that's pretty much how a CD or DVD works. Those little pits and lands has a little laser light that reads it, and yeah, that's it, okay? So the next page there has more information about the difference between digital and analog signals. Please read over that. Also, some societal, cultural things about the implications of ever-increasing data storage capabilities. Really, really cool stuff there to read about. So that'll be it for the notes for Tuesday. Actually, hold on. You know what? I think we might have one more video. We'll see, though. But that's it for digital and analog.